Welcome to a lesson with Dr. Powell. Let's talk about how we can use this left-right inverse pair idea for projections to talk about orthogonal projections. Like, for instance, what if we have a vector w that we want to orthogonally project onto a vector v, such that the light that's being cast right here as a 90-degree angle to the vector v. How's that going to work? Well, remember that um, the function g, or the linear transformation g, the range of it was kind of what we were trying to get onto, right? The ground, the vector that we're projecting onto kind of could represent g. So we'll just put that. Now think about the kernel of f. We want the kernel of f right here to be perpendicular or orthogonal to -1, 4. Hmm. Well, it's kind of interesting because -1, 4 itself as a matrix of this size, its kernel is orthogonal to -1, 4 because its kernel, because as a function, this is just a dot product. And dot product equaling the zero, well, actually, just an R1, just the number zero. Um, Everything that's orthogonal is the same thing as the kernel, right? So, so that tells me if I want, if I want kernel of f to be orthogonal to this, this should be the matrix itself, right? So basically, this should be a good matrix for f. So this is a good choice for f and g, except for one thing. Um, we need the g to be a right inverse for f, and we can't quite get that as it is, because what happens when we do that? Because when we do this, we're not going to get the number 1. We're going to get another number. We get 1 plus 16, you're going to get 17. So to offset that, what we can do is we could just divide this side by 17, divide that side by 17, and just have a 1. All right. So this would be a nice deal right here for where this is your f, and that's your g. Let's see, right? Okay, so what we could do is so if we wanted to think about projection, I'll remember what we do is we swap this. We say g of f, and then in front, we just, we can put the scalar out there. Now, realize what this scalar is right here. This scalar actually represents, it's just the dot, since we're letting the dot product be equal to, so this is just the dot product, right, of these two guys, this matrix multiplication. This 17 is just the dot product of -1, 4 with itself. So I'll kind of keep that in mind. So we can remember that, but but as we swap these orders, this 1/17 as a scalar can just come out front. So this right here will represent the matrix function, which we can plug a vector into, such as w, and see what the projection is, what that projection vector is, just looking for what that guy would be right there. Okay, w projects on. So this is what we're after right here, 1/17g of f. Now, how can we get this? Remember, here, what we could do is we could simply just look at this right here. We're thinking of v as being a column. Now, if v is a column, v transpose would be like a row. Notice how we're swapping these two guys anyway. So like f is a row, so it's over here. So this is like, this vt is kind of like an f. And then this v right here is kind of like your g as a column, -1, 4. So you can think, in fact, you see it right here, this g and f. But to offset, remember that, but also in this, we have to have a 1/17 somewhere. You could put it on the f or the g, or you could square root it and put it in both of them. But well, whatever else, this 1/17 kind of comes into place. So this right here is precisely what we were just discussing, that right there. And notice what we're doing. We're just sticking w as a column into that matrix, multiplying by this as a function, the this is G of F. So really this just gives us the projection. Now there's various ways of computing this, for sure. I mean, notice how we grouped it, V, VT, W, and so forth. Now VTV, now realize that's actually just the dot product of V with itself. So we could have put the V out here and then did VTW to begin with. And then we could just divide by VTV overall, okay. VTV, and we could have done this product first if we wanted to. Now this product right here, remember, both of these vectors are being thought of as columns. So this is like a row and a column. This is just a dot product. This is the dot product of V and W. You could say V dot W, and this is V with itself, V dot V, and then you're just multiplying it. This is actually just a scalar, and it's multiplied to the vector V. It's just a scalar multiple of V, which should make sense because this is just a straight line. And all the vectors in it are just scalars, scalar multiples of V. And this is the scalar multiple that we're after. So we could just go ahead and compute that. And so taking a look at these two vectors, we can just take the dot product between them. So 2 and -1 would be a -2. And the 3 and the 4 would give you 12. Okay, so that would just give you 10. And then, so you take the dot product, that's 10. Then you divide it by V dot V, which we already found was 17. So we have just 10 over 17 times the vector V. All right, that's it. So what we just computed was the orthogonal projection of W onto V. We can write that vector, this vector right here, we could write it as proj, or projection, of a vector, the vector V onto, or vector W, excuse me, vector W onto the vector V. Notice how we write V lower. It's like W's on top of V or coming onto V. And this, the output of this guy is a vector. So that's a vector. In contrast to something like this, when we take like the component of W on V, that's a length, but this is a vector. So this is a vector. And this guy right here is a length. And the way we compute this, the length is actually given right by this itself. This is, well, not quite given by this. It's a little bit different. It would be given by this if V happened to be like a unit vector, right? Then it would be given by this. So it's a little bit different. However, because V is not a unit vector, this is a little offset. This is the scalar that we multiply to V. So it's a little bit different. So the computation of comp of W on V, first what we would do is we'd make V into a unit vector. So we'd say something like 1 over the length of V times V, and then we would compute this length. Now, so we would replace V with this, it being a unit vector. If you dot this with itself being a unit length, you'll just get 1. So really you can ignore the bottom. And then it just becomes a dot product. This dotted with W, and that actually would be equal to the length. But you see there's a difference between, this is the component length of W on V, but this video primarily actually was about this guy right here, the projection of W onto V. Thanks for watching.